We have discovered more than 5,000 planets beyond our solar system. Not 500, 5,000. That's like a galactic census, something we couldn't have even dreamed of 30 years ago. Every new speck of light captured by a telescope could be a whole new world. A world with two suns, where the sunset never truly arrives. Or a frozen, endlessly dark orb drifting through interstellar space. It sounds like endless variety, but there's one problem. Most of these worlds are, surprisingly, quite predictable. Hot Jupiters orbiting closely around their stars, super-Earths, rocky planets several times more massive than ours. To navigate this cosmic menagerie, scientists divide their discoveries into three broad categories. The first includes worlds that could potentially support life. Our best hope? The search for Earth 2.0. The second group consists of killer worlds, extremely hostile places where we'd be instantly incinerated or torn apart. But then there's a third category, and this one captures our attention. These are planets that don't fit into any existing model. They break our theories. They are anomalies. More precisely, not just anomalies, but objects whose behavior leaves scientists baffled. These are the discoveries that push science forward, forcing us to ask the fundamental question, how is this even possible? Today, we're stepping into a room filled with curiosities. We'll explore a planet that plays hide-and-seek with our telescopes, appearing and vanishing without any warning. We'll visit a world that heats up from furnace-like temperatures to those of a star's surface in just 6 hours. And we'll witness two planets in the same system hurtling toward each other, gearing up for a collision that seems unavoidable. Our first stop is a world that seems to have a mind of its own. A world that simply disappeared one day. How can an entire planet blink out of sight? In 2009, astronomers watching the star Kepler 413 spotted exactly what they were looking for: a tiny, regular dip in brightness. It was a transit. A planet passed between us and its star, casting a shadow. According to calculations, it should cross the same path again in 180 days. Scientists pointed their telescopes and waited, but nothing happened. At the scheduled time, the star shone just as steadily as ever. The planet they had just discovered simply vanished. It's like spotting a ship on the horizon, looking away for a moment, and then turning back to find only empty water. At first, everyone thought it was a mistake. Maybe the initial signal was just interference, some random glitch in the equipment. But then, 800 days after the first detection, the planet showed up again. It crossed in front of its star 5 times, right on schedule, and then vanished once more. It became clear. This wasn't an error. Something physical was happening, something we couldn't explain. How could an entire planet, a gas giant 25 times more massive than Earth, play hide-and-seek with us? The answer turned out to be even stranger than the mystery itself. It wasn't the planet disappearing. It was its orbit that vanished. Here's a spinning top on a table. At first, it spins steadily, but as it loses energy, its axis starts to trace a cone in the air. It wobbles. The same thing happens with the orbit of Kepler 413b. This planet orbits a binary star system, and the gravitational tug-of-war between the two suns causes the entire orbital plane to tilt and wobble in space. This cycle takes 11 years. During that time, the orbital plane shifts by 2.5 degrees. A small change, but enough so that from our vantage point on Earth, the planet no longer passes directly in front of its star. It's still there, only its shadow now misses us. But this wobble in the orbit is only half the problem. The real trouble lies with the planet itself. This gravitational dance also makes its own axis of rotation unstable. Earth's axis wobbles too, a slow process called precession that takes 26,000 years and drives ice ages. On Kepler 413 beta, everything happens thousands of times faster. Its axial tilt swings up to 30 degrees. Wait, 30 degrees isn't just a change in seasons, it's climate chaos. Imagine the North Pole on Earth shifting to the equator spot in just a few years, then moving back again. Such drastic tilt shifts trigger planet-wide hurricanes and storms so intense that Jupiter's Great Red Spot looks like a gentle breeze. These atmospheric whirlwinds collide with such force they can blast gas into space, only for gravity to pull it back later. A world wobbling like a drunkard. That already sounds extreme. Yet, it's at least understandable when tangled in the complex gravity of a binary star. Strange, but it makes sense. Still, some worlds defy even that twisted logic. They endure violence on a relentless schedule. Our next subject is a planet that plunges into sheer hell every few months. Meet HD 80606b, a gas giant 4 times the mass of Jupiter, orbiting a star much like our own Sun. But that's where the similarities end. Its orbit isn't a near-perfect circle like the planets in our solar system. Instead, it traces a wildly elongated ellipse, more like the path of a comet. For most of its 111-day year, this planet stays far from its star, roughly the same distance Earth orbits the Sun. At that point, it receives a comparable amount of heat and light. You could say the conditions there are almost temperate. Then the nightmare begins. Over the next 55 days, the planet plunges towards its star. Its distance from the blazing sphere of plasma shrinks by nearly 30 times. Meanwhile, the energy pouring down on it surges by 800 times. Imagine taking Earth and, in less than 2 months, moving it into Mercury's orbit, right into the heart of the solar system's inferno. And here's something hard to believe. At the moment of closest approach, within just 6 hours, the temperature on the planet's day side rockets from 900 degrees Fahrenheit to over 2,000. Wait, 900 to more than 2,000 in 6 hours. That's a jump of 700 degrees. It's like opening an oven door, then instantly finding yourself on the surface of the Sun. The planet's atmosphere expands so rapidly from that heat shock, it creates a shock wave. A real supersonic blast racing around the planet at 3 miles per second, circling it again and again. This isn't just weather, it's a global concussion. The shock wave from this explosion heats even the planet's night side. It bounces back, sending the whole world vibrating like a bell struck by a fiery hammer. And this apocalypse repeats every 111 days. Cyclic, predictable. This isn't a random disaster. It's the planet's life schedule. But why does this planet follow such a self-destructive orbit? Most likely, it's the lone survivor of its system. Near its star, there's a companion star. Long ago, the gravity of this second star invaded the young planetary system, flinging all the other planets into interstellar space and warping the orbit of this solitary giant beyond recognition. A lonely planet tossed by gravity from scorching heat to freezing cold. That already sounds terrifying. But what if the danger involves not just one world, but an entire system? What if 2 planets race toward each other so closely that their very worlds are torn apart? In the Kepler-36 system, located about 1,500 light-years from Earth, this isn't a hypothetical scenario. It's a schedule. 2 planets orbit there, a rocky super-Earth and a gas-rich mini-Neptune. Every 97 days, they perform a deadly dance. The planets draw as close as 1.9 million kilometers apart. To put that in perspective, that's 20 times closer than the closest distance between Earth and Venus. It's just 5 times the distance from Earth to the Moon. If one of these planets had oceans, its neighbor would loom so large in the sky that it would cover half the horizon, while tidal waves kilometers high would sweep across continents. At their closest approach, the gravitational pull between them becomes 13 times stronger than the force between Earth and the Moon. The outer planet, Kepler-36c, is a gas giant with a mass 7 times that of Earth. The inner one, Kepler-36b, is a scorching, rocky world with surface temperatures soaring above 700 degrees. It weighs nearly 4 times as much as Earth, more precisely, 3.8 times. But its mass isn't what grabs scientists' attention. Its density is unusually high. This led researchers to propose that Kepler-36b is a chthonic planet. In other words, it's the exposed core of a former gas giant, stripped of its atmosphere by its larger neighbor during one of their close encounters. The bigger planet literally drained away its gaseous envelope, leaving behind only a heavy, fiery heart. This gravitational grip is far from beautiful. It's torture. Every 97 days, the gravity of a massive neighboring giant tears at the crust of this rocky planet. Its surface cracks like fragile eggshells. These aren't earthquakes as we know them. They are tectonic plates, continent-sized, shifting and crumbling in real time. From the fractures, thousands of volcanoes erupt all at once, pouring rivers of fire over an already hellish landscape. This world devours itself in a relentless cycle, driven by the gravitational whip of its neighbor. A geological hell that operates like clockwork. But how long can this dance on the edge of a cliff last? The answer? Not very long. The entire Kepler-36 system behaves chaotically. That's a scientific way of saying we can't predict its future precisely over long times. Even the slightest change in starting conditions sends its evolution down a completely different path. It's like trying to guess where a leaf torn loose by a hurricane will fall. Yet even in this chaos, one pattern stands out, almost inevitable. Computer simulations running millions of possible futures for this system all return the same chilling forecast. There's a 91% chance the two planets will collide. This isn't just a theory, it's nearly a sentence. The system has a rough expiration date, about 70 million years. After that, collision. We have witnessed violence and chaos, systems programmed to destroy themselves. But the universe is not just about destruction. Sometimes, in the heart of all this instability, something incredibly beautiful takes shape. Something so immense that its rings could swallow our entire inner solar system. Yet, this beauty comes at a cost. There's a place in the universe, 434 light-years away, where night never truly darkens. Orbiting there is an object astronomers have unofficially named Super Saturn. It's either a massive gas giant or a brown dwarf, a star that never gained enough mass to ignite. It's young, only about 15 million years old, and it's surrounded by a ring system so vast that our Saturn looks like a faint shadow in comparison. The numbers here defy imagination. This planet, J1407b, has at least 37 distinct rings. The outer edge of the largest ring stretches out to a distance 640 times the radius of Saturn's rings. If a system like this orbited where Saturn does in our solar system, its rings would be visible from Earth with the naked eye, brighter and larger than the full moon. They would dominate our night sky with a giant glowing arc. And this unimaginable structure of dust and ice spinning around the giant planet carries more mass than the entire Earth. But the most fascinating secrets lie within these rings. Astronomers have detected a wide gap inside them. This isn't a coincidence. Such a sharp gap usually forms because a moon clears its orbit with its gravity. Calculations suggest that within this gap likely orbits an exomoon with about 80% of Earth's mass. And it's not alone. Signs point to at least 2 smaller bodies nearby. This isn't just a set of rings. It's a massive protoplanetary disk where new worlds are being born right now. Computer simulations reveal something astonishing. These moons might have a comfortable temperature. Heat from their parent star, combined with residual warmth from the still hot planet, could be enough to sustain liquid water. Pause for a moment. Try to picture this. The sky of a hypothetical moon inside these rings. Above you hangs not a tiny dot, but a colossal disk of its host planet, 70 times larger than our own moon. It dominates the horizon, casting a faint glow that reflects off the rings and bathes the landscape in eternal twilight. Stretching from horizon to horizon, glowing arches span the entire sky. Dozens of these arcs, inner rings of the system, appear from the side like incredible highways of light. But this world wouldn't be quiet. The gravity of a giant, 20 times more massive than Jupiter, tears at the moon's interior. Tidal forces ignite constant volcanic eruptions and massive ocean waves, carving a tidal zone hundreds of miles wide. A world of raw, fierce, and unimaginable beauty. But as with all beauty, this one comes at a price. Massive ring systems like these are inherently unstable. Gravitational pulls between particles, the pressure of starlight, and the influence of forming moons, all of these forces slowly but surely tear apart this majestic structure. On a cosmic scale, its lifespan is brief, just a few 100 million years. In fact, it's already breaking down. Ring particles either fall onto the planet or clump together to form new moons. This breathtaking spectacle we see from afar is just a fleeting, brilliant moment in the life of a planetary system. A moment we are lucky to witness. We've reached the end of our journey through the strangest worlds. It all began with a simple question. Why does the universe create such anomalies? We've seen planets that should have burned up, but survived. Orphan planets drifting alone in eternal darkness. Star systems set on a collision course with their own destruction. And finally, that fragile, fleeting beauty, more incredible than anything we could have imagined. And now, the answer is starting to take shape. We searched for order, something like our own cozy solar system, repeated somewhere else in the cosmos. Instead, we found chaos. We found violence. We found beauty born from catastrophe. Maybe the biggest anomaly is our very idea of what's normal. We thought we were hunting for exceptions to the rules, but what if these exceptions are the rules? What if the universe, by its very nature, is an endless generator of unpredictable, unstable, and astonishing designs? Every new discovery, every mystery we solve, doesn't close the book of knowledge. Instead, it opens a new chapter filled with even deeper questions. Each so-called anomalous planet doesn't tell us, here is the answer. It asks, what if this is possible too? We thought we were searching for answers, but it turns out we're just learning how to ask the right questions. And this journey has no end, no final map, only an endless horizon.